I should mention though that there are, for the MEM competition, cash prizes of I believe 500, and for the COE competition, I believe it adds up to a potential of 6,000 for the top place team, if they get all three of the prizes. Take it away.
Hi everyone, we are Senior Design Team 15. I'm Alex, this is Chris, Barry, and Josh. We are the Drexel Flying Dragon engine team. So a little bit of background about our project. It started 2 years ago by our advisor, Ryan Miller. He was trying to set the world record of 99 miles an hour. He went to ECTA in Ohio, broke the record there, 82 miles an hour. Last year they tried to do it again, didn't get to race, so they couldn't really try to break that. Currently there's 2 teams, the engine team, us, and the frame team back there, working on this bike right here. The problem is we would like to try to develop the engine so we could theoretically propel a rider to 100 miles an hour. Not necessarily beat the record, just make the engine so it can do so. We have some goals down here. First goal, try to reach 20 horsepower or more. Secondly, work with the frame team to develop this prototype functional and safe. And then last, we want to try to set the records. That'll be in a month from now, I think. So here are our stakeholders. First and foremost, Ryan Miller started the project. Dave and Tyler, also alumni. Our advisor, Todd Ventura, both teams, Drexel University, all our sponsors, and the motorcycle industry in general. These are the needs of our stakeholders. First, create as much horsepower as possible. Secondly, develop a safe prototype so we can use it for racing down the road. Apply our knowledge learned throughout the course of our time here at Drexel, and also try to make this bike as advanced as we possibly can. These are the rules and regulations set out by SCTA, ECTA. We follow these while we're developing bikes so we can make sure that Chris is safe as he's flying down the road. We met all of these regulations, so we should be good to go when the time comes. Here's a mission statement. We first wanted to try to beat this record, but we could not get there before the year was over. We wanted to try to make our engine go to at least 20 horsepower for 5 minutes to kind of simulate that record breaking.
So basically the methods in general that we needed to go over is we needed to study the flow of gases through our system, how we could generate more power and figure out where power is being lost at. Basic understanding of most of our engineering classes at the school, such as heat transfer, fluid dynamics, material strengths, and thermodynamics is what we use to figure out all these issues. So we began our project with a method of reverse engineering. We looked back in the past 2 years' teams to see what they had to offer to the actual engine and what they actually did with it. The starting engine when we received it only had 13.6 horsepower, 13.06 horsepower, and the only bike that was able to compete only achieved 82 miles an hour. Basically, the wind resistance just overtook the power that the engine was able to produce. We also looked at the designs of the frames that they had in the past years to see where their engine placement was, see if the engine points and the motor mounts were strong enough to hold the engine in place. We noticed with the second year's bike, the engine wobbled around a lot, so there was lots of power being lost and not transferring to the wheels. So we had to work very tightly with the frame team to make a good design for the engine to be securely mounted in place in the proper location. Once we figured out a good frame design, we knew after doing a CFD analysis on the frame design that we needed to achieve a minimum of 12 horsepower on concrete and 15.77 horsepower on the salt flats due to the difference in rolling resistances of the two surfaces. Give me 1 second and I'll play a video for you of our final dyno.
Leave it going.
Presentation.
Ambiance.
Okay, so as we said earlier, we set our power goals. We need at least 15.77 horsepower. We factor in a safety of 10% to account for any losses that we couldn't account for, and then so we need 17.35 horsepower to beat to match the record, but we don't just want to match it; we want to beat it. So we're aiming for 20 horsepower. Essentially, all we do to do that is we increase the airflow of the engine. These are some of the specifications of the engine. We're aiming for 12,000 RPMs, where our peak power is. It shows our sprocket sizes. Anthony will go into that later about how we calculated what's ideal for these situations. Essentially, an engine is an air pump. The more air you can move in and out of the engine, the more fuel you can burn, hence the more power you can make. I'll also go into this diagram in more depth later.
So, the beginning of the system is the air intake. Since we were in a class where we couldn't use force induction by use of a turbo or supercharger, I decided to design a ram air induction system for the motorcycle, which basically takes the air as you're driving. The faster you drive, the more air that flows right into the intake. But the only issue with this is you need to make sure that the air doesn't reach any type of sonic speeds within the system, because then it could cause like a bottleneck and stop the engine and starve it. And also, you got to make sure there's not too much restriction, because earlier the bike wouldn't rev past 9,500 RPMs because there was just a screen on it and it was too restrictive for the bike to rev out. So we needed to make sure that this intake was streamlined, get all the flow that we needed, and make sure there was no restrictions. Here's a picture of the intake on the screen, and you can actually see it right in front of you as well. It was created with 3D printed parts, and we just did our proper heat shielding that we needed to make sure it didn't melt or it caused any type of damage to the motorcycle.
Okay, so this is a picture of down the bore of our cylinder, and what makes this different than your conventional four-stroke engine is that there are no valves. So as the piston moves up and down the cylinder, it uncovers and covers certain ports. And by changing the shape and location of these ports, we can maximize our airflow and essentially change our engine timing. And this diagram here is very important to the function of the two-stroke engine. It uses a tuned exhaust chamber, and the inherent flaw of the two-stroke engine is that you lose fresh intake gases out the exhaust while the piston is at bottom dead center. So to combat this, you use a tuned pipe, which actually reflects a sound wave back, which keeps that charge in the cylinder so it's ready to burn. This is the expansion chamber we ended up going with. We had another one from FMF, but what they do is they change the size and the shape of it to tune it for a specific RPM. And the fatty one was much better for our needs.
So for the gearing, the first step was to take a look at the transmission and figure out exactly what type of ratio each gear had. Then our approach was we would take a look at the sprockets, the rear sprocket and the front sprocket, and figure out how many teeth we would need in order to hit our target speed at our maximum power RPM, which is 12,000 RPM. So here you can see our governing equation to figure out what our speed is based on our ratios. And we've calculated in this chart, as you can see, different speeds that we're going to be able to hit in each gear, giving us a target speed of 108.7 miles per hour in 6th gear with our current gear ratio setup. So some other modifications we made, we were able to salvage our controls from one of the previous motorcycles, which was nice. We didn't have to buy extra parts we didn't need. Cooling system, we decided to go with engine ice. It's a very good coolant, widely used in two-strokes. Also, we decided to go with the gear-driven water pump instead of electric. It's just way more efficient. Secondly, our reed valve, we went with carbon fiber, improved the air velocity, and it increased our maximum horsepower overall. Next, our carburetor, we decided to go with the PWK 28. The reason for this is it's a D-shaped carburetor, and what that means is that there's basically three main different shapes. There's a D shape, there's a rectangular shape, and then there's circular. The D shape is kind of like the best of both, circular and rectangular, whereas we're going to be able to achieve maximum RPM power, regulate the fuel in there, as well as have enough torque down the low end to be able to propel us forward. So we decided it was just the best of all the options. Next is the fuel. Per our regulations that we were given by ECTA and SCTA, we'll be using U4.4 racing fuel by VP Racing. This is 103 octane leaded fuel. It's pretty much the highest octane that we're allowed to run per regulations, and it's so far achieved our maximum power out of different fuels we tested. So for the embodiment, we did a lot of 3D modeling to do this project, to collaborate with the other team, mainly SolidWorks. Once we had our frame designed, we took the motor and we were able to utilize the 3D scanner down in the UG lab. We took a scan of it, placed it into the frame, make sure everything fits, and that way when we started to route our exhaust and our intake and everything else, we knew that there wouldn't be any issues when it came to putting everything together and making sure that everything was going to work right. So here you can see some of the different components of our final design. The exhaust, the intake, engine. This is pre-paint, obviously. This is right after fabrication. So for our context and impact, first is going to be economic. So we developed a prototype within our budget. Again, luckily we didn't spend too much money on our motor. We were able to outsource a lot of it and have a lot of our work donated. We had free dyno pools. We had our porting work done for free. Just helping out our sponsors with getting their name out there, putting stickers on the bike. As far as environmental impact, we are using lead fuel, which in theory is harmful to the environment. However, this is completely negligible in this case because there is so little emissions with doing a run on this motorcycle that it just really doesn't affect the environment negatively very much. For social impact, we're trying to increase the attention overall for just land speed racing as a sport, get people more interested in motorcycles in general, and also get students involved in STEM projects. For example, something interesting like this, we could definitely see being able to convince high school students to get into engineering or any type of STEM related field study. For ethics, we were adhering to our safety regulations that were put forth again to make sure Chris is going to be absolutely safe while he's riding this motorcycle. We didn't overshoot too much, like we're not going to go for like 140 miles per hour because it's just a little too much for this frame.
So safety considerations. Myself being the rider, it's pretty important to me. I'll be wearing a full suit as well as a full face helmet, gauntlet gloves, all that. As far as the motorcycle though, there's certain safety factors that we have to consider, such as a chain guard. So in case there is a break in the chain, it's contained. It doesn't actually. One, it protects the motor. Two, it protects myself as a rider. There's a great deal of heat. And the fact that I'm straddling this, it needs to be confined or directed elsewhere. So there's some heat shields. They also act as guards to protect my legs from other things that might come flying apart. But in general, as far as safety, it's about myself, and then as well as protecting the motor in case of other failures. So the two teams, it's crucial for them to communicate with each other between the frame and the motor. We need to be developing at the same time as far as locations, placements, mounting, and there's a great deal of communication that needs to go on between the two teams. We achieve that through our 3D modeling and a lot of collaboration. There's also a great deal of budgeting that has to be done between the two teams as we share the same funding. So that has to be taken into consideration as one team can't have all the money. And then all the subsystems must work together when finally designed, and it needs to come together as a full working prototype. This here is a graph, our dyno graph showing our initial dyno from when we got the motor from the first and second team's condition, which is the shortest one there. Our second line on here. This is the first one at 13 horsepower from the original team. This is after we had the motor running properly, and this is our final achieved horsepower and torque at 20.26 and 10.11 torque. So we achieved our goal and achieved a 55% increase in horsepower from when we initially received the motor. So we are 100% budget and hit all our goals, and we are within regulations and tech and all that. So we will be competing with this motorcycle. Future work is developing a carbon fiber intake to be lighter, smoother on the inside, better flow. A custom exhaust. So as we said, we chose a pre-made expansion chamber due to the fact that custom making one. It does have advantages. You can tune to a more specific RPM, but as far as the limitations that we have to produce this project to where it is now, we went with a stock pipe. And then other things such as revamping some components, such as things like kill switches and stuff that we used for previous models of the bike. And then obviously to compete with this motorcycle. As far as team management, like I said, there was very much communication between the two teams as we needed to work hand in hand the entire project. We used Liquid Planner, Google Drive, Google Hangouts for team meetings. Team leaders, we have Ant was a team leader in the fall term, and then Josh took over winter and spring terms. Anthony handled finances. Originally we had, had subsystems and divided up between team members, but that all kind of mushed together as we started to work through the project, and people, we all worked together throughout, and there was much collaboration between the two teams. So here's our Gantt chart showing our progress. We were on schedule the entire project. We had a few hang-ups with financing, but other than that, we were on schedule and spot on. Here's our budget. We have a few big sponsors, but in total, we are on budget with we're on budget with between building and have leftover for travel and event costs. So, and here's the references. Here's our sponsorships. Big thanks to FSAE for workspace and tools and all that. Bikeworks for our dynoing. Millennium Technologies, they were reporting. And then our grants from Boeing and Inspire Performance. So, thank you very much.
Questions from the audience?
What motorcycle did this engine come off of? And what was the standard top speed of that bike? You know?
This engine's off of the Kawasaki KX100. The bike's originally built for off-roading, and the way the gearing is set up, it really only achieves about maybe 65 miles per hour top speed, because off-roading is more geared towards fast acceleration and being very agile.
It also has like a huge upright rider position that, when you're standing on it, you can barely touch your feet to the ground.
So I have a question. Two questions actually. Can you explain to me, so you were using the laser scanner down in the UG lab, and then from there you came up with a design which then you manufactured, is that correct?
We used the scanner to figure out for the modeling of the frame. Basically, we needed to know exactly where the engine was going to be located and how much space we needed to make for the frame team for our intake system. The biggest challenge was trying to keep the intake within his legs very narrow, so we needed to know exactly where the motor was going to go on the bike.
So what is the precision of the laser scanner that you used? What was the accuracy?
I'm not sure what the actual accuracy was, but since a lot of the locations weren't needed to be that accurate, it just needed to be like within a half an inch either direction. That's what we needed. So we knew that the scanner was going to be able to do something much more accurate than what we needed.
Are you sure about that?
It was more so for clearance rather than tolerances. So we needed to make sure that nothing was going to be interfering with the engine rather than precise fitment. The only precise fitment that we actually had was the motor mounts, and we were able to model those off of the previous frame. So it was very effective in helping us make sure that actual frame cleared everything we needed to clear.
So how many times have you actually test driven the vehicle at this point?
We haven't been able to test drive the vehicle yet. We have done several dynos to ensure that the motor is strong and sound. Before the winter term, we produced, I think, about 45 dynos with the engine to get it at a decent point, but then when we sent the motor out to have certain modifications done to it, and we got it back, we did, I think, about 15 runs since then. So it's ran several times, and the engine is a very solid thing. We just needed to work on all the final tweaking of the frame with the frame team and we're going to look into possibly going to Willow Grove Air Base to test it out, to see how far we can go, how fast we can go, using a radar gun and also GPS monitoring from like a bicycle. But that just hasn't happened yet.
And so what kind of accuracy would you expect when you use those kinds of measurements?
We'd have to actually look at the accuracy of each item. The radar gun is outdated and old, but we are going to just look up the specifications online to see how accurate it is. But the true accuracy comes at the actual competition, which is based on time over distance. There's a set distance that they know. They start recording with like a laser, and then they stop recording when you cross that second laser.
So
it's-
how close do you think you can predict what your final performance is going to be?
100%.
How close? It's not.
I mean, we set a set distance, you measure time between the distances.
No, right, but my point is the fact that you haven't tested the vehicle, right?
Okay.
You don't quite know what the precision of the instruments you are going to be using to measure when you actually test the vehicle to be able to measure the final speed that you're able to achieve. And so the question is what do you think is the likelihood of you actually hitting the target sort of desired speed, given the fact that you haven't essentially done the measurement error analysis compared to what the precision of whatever the competition actually uses to do the measurement.
We're pretty certain we're going to be able to make the speed just because we use that factor of safety. I don't know if you were there for that slide whenever we showed up. The horsepower needed to achieve the maximum speed that we're looking for is 15.77 horsepower on the salt flats, and that's with the rolling resistance, with the weight of the rider, with the air drag or the coefficient of drag, and all the forces that are needed to be overcome. So to take that into account, we used a 10% factor of safety, and our goal initially was going to be 17.3 horsepower. That way we know if we have that horsepower making it to the rear wheel, we should easily exceed the speed of 100. But then we decided we wanted to beat the 100-mile-an-hour barrier, so then we did modifications to get up to 20 horsepower. So we're actually 5 horsepower or 4.23 horsepower over what we need to achieve that goal of the speed. And if there are any losses that we didn't take into account for, other than the rolling resistance and the drag, then we have that 4 horsepower barrier or cushion.
But you haven't actually tested the whole system integrated together.
Well, on the dyno, it tests the full system. Did you see the dyno video?
We're a little short on time, so we'll have to leave it at that. I do have one other question. Our other team is in the room, is that right?
Yeah.
Okay, great. So we've got another 2 minutes before they start, so I'd like to take up 30 seconds of that time just asking you to give us a window into your systematic design process, because you made lots of decisions. Your outcome is very impressive, a 55% increase. From what you presented, you were showing mostly the results, but I'm curious how you got there. So pick a component. Maybe it's the exhaust, maybe it's a little bit of your intake, and give us a window into how did you get from concept to embodiment detail to the final product.
The intake, there's very multiple generations of the intake. At first, we wanted to make a really short intake tract, and then when we tested it on the dyno, we realized it choked the motor. Then I started looking into flow inlet design into a pipe. There's lots of losses that happen with just a straight pipe with straight edges, but if you curve that pipe, there's minimal losses. You reduce it by like about 90%. So once I found that elliptical profile, I started making a 3D model of a velocity stack. 3D printed it downstairs in the UG lab and test fitted it on the motorcycle and used it for a dyno. I made 3 different lengths to see which length would be the optimal length with 3 different ratios. There was a 1-to-1 ratio with the height of it, and then there was 1 to 1.5, and then a 1-to-2 ratio. And each time we tested it to see how power was gained and how it improved. We found that the 2-inch system was the strongest, so we were going to go with the 2-inch velocity stack. But then it became the problem of trying to have an enclosed intake system. You need at least, I believe it's 3 or 4 times the actual size of the engine combustion area. You need that volume in your intake manifold, or else you're going to choke the engine out. So I had to use calculations inside of the Creo.
So that gives me an idea. I appreciate that. So in I mean, you've been through 435 and the Organ-Eppinger method, and there's one way to do it where you have all of the specifications and you iterate and evaluate and go around the circle, et cetera. So it sounds like I could characterize your approach in one of two ways. One, trial and error with a bit of luck. Two, you could say that it was iterative empirical testing, which sounds a lot fancier. And it sounds like you've done enough of the quantitative efforts towards that I'd probably put you in the latter camp. So again, impressive results, and thank you for your presentation. Let's thank them again. Let's have our next team come up.